Welcome back. Let's learn how to solve basic uniform motion problems. Alright, so the last application of solving basic equations that we are going to look at here in algebra, at least for right now, is the ability to solve basic uniform motion problems. But what exactly is uniform motion? Well, uniform motion describes an object that is traveling at a constant speed in a straight line. In other words, an object is moving in such a way that its speed and its direction do not change. For example, consider a car that is traveling at a constant speed of 60 miles per hour, meaning that it does not change from that speed. It's always 60 miles per hour, and it's traveling at that speed along a straight road. We would say that that car is in uniform motion. Okay, so the car is not accelerating, it's not slowing down, and it's also not changing its direction. It's going 60 miles per hour in one direction. That would be uniform motion. And when an object is traveling in uniform motion, such as this car, we can quickly determine how far it travels given that we know its speed and the amount of time spent in motion, or the amount of time traveling. So in our example here, if this car in uniform motion is traveling at 60 miles per hour for a total of 3 hours, we could determine the distance that it would travel in that amount of time. All we would have to do is multiply 60 miles per hour by the amount of time, 3 hours. Alright, so the distance that the car travels would be equal to the 60 miles per hour multiplied by the 3 hours. And that should make sense, because if this is a rate of 60 miles per hour, then you can multiply that by the number of hours that the car spends traveling, and that will result in the number of miles that the car would travel in that amount of time. And of course, the amount of miles is a value of distance. Okay, so 60 times 3 is equal to 180, so we get that the distance is equal to 180 miles. Okay, so that's a very nice calculation that we can perform for an object in uniform motion. In fact, we can generalize this calculation for any scenario involving uniform motion with the following formula. The formula is d is equal to r times t, where d represents the distance traveled by the object in uniform motion, and then r is the rate of travel. So in our example with the car, that was the speed of 60 miles per hour. And then you multiply that rate of travel by t, which represents the amount of time spent traveling. So in our example with the car, that was the amount of 3 hours. Okay? And so we can use this formula to solve a variety of uniform motion problems. And that's what we're going to focus on for the rest of this lesson. We want to take a look at different problems involving scenarios of an object in uniform motion where there's some piece of information that we don't know. But we are able to find it by using this formula to set up an equation that we know how to solve using the equation solving skills that we developed earlier in algebra. Alright, and so let's take a look at our first example. For this example, we are told that a cross-country runner can run 6 miles in 45 minutes. Assuming uniform motion, what is the runner's running speed in miles per hour? Okay, so in this problem, our object in motion is a person, so not really an object, but it's still something that is in motion, specifically uniform motion. We are assuming uniform motion in this problem, meaning that the cross-country runner will be running at a constant speed throughout the entire race, which realistically probably does not happen, but we are going to make that assumption in this problem. And our goal here is to figure out what that constant speed would be. Right? We want to know what is the runner's running speed in miles per hour. And in order to find that, we need to make use of these other pieces of information. The fact that the runner is running 6 miles in 45 minutes. Okay, so to solve this problem, we need to make use of the uniform motion formula that we just looked at. We know that the distance traveled d is equal to the rate of travel times the amount of time spent traveling. And in this case, we do not know the rate r. Right? That's what we want to solve for. We do not know the running speed in miles per hour. So when we set up this equation, r is going to be the variable that we're solving for, which means that the other two variables we should know the value of. And in this case, we do. We know that the runner is running 6 miles, that would be an amount of distance, in 45 minutes. So that would be the amount of time. All right, so let's write down these values that we know. We know that d is equal to 6 miles and we know that t is equal to 45 minutes. Now, something you need to pay attention to in these problems is the units that you're working with. Specifically, what I mean by that is the units for your distance should match the units in the rate. So in this case, we're working with miles, and our rate is in miles per hour. So that's good. Those two units match up, but then the units for time also need to match up. In this case, we were given an amount of time in minutes, but our rate is in miles per hour. Okay, so because we want to solve for that speed in miles per hour, we want to make sure that our amount of time is also in hours. Okay, we want to express it as an amount of hours. And so in order to do that, just remember that there are 60 minutes in an hour, so we could convert t to be an amount of hours by dividing those 45 minutes by 60 minutes. Okay, so 45 divided by 60 would be the amount of hours, which if you reduce that fraction, both 45 and 60 are divisible by 15. 45 divided by 15 is 3, and 60 divided by 15 is 4. So we would say that that is equal to 3/4 hours. Okay, so now our amount of time is in hours, which is what we want. So now when we set up this equation and solve for the rate r, which will be the speed, we know it will be in the correct units because our distance is in miles and our time is in hours, which means that that rate would have to be in miles per hour. Okay, so let's set up the equation here. We know that d equals r times t, and our amount for d is 6. So we have 6 is equal to r, the rate that we don't know, that we want to solve for, multiplied by the amount of time, t, in hours, which is 3/4 hours. All right, and so now, to solve for r in this equation, we need to get rid of this constant being multiplied by r, and so you could divide both sides by 3/4, or maybe an easier way to go about it is to multiply both sides of the equation by 4/3, the reciprocal of that fraction. All right, whatever you do to one side of the equation, you have to do to the other. So if we multiply both sides by 4/3, 3/4 times 4/3 will be 1, right? 3 times 4 is 12, 4 times 3 is 12. You have 12 divided by 12, which is 1, and then 1 times r is just r. So what we find here is that r is equal to 4/3 times 6, right? We have 6 times 4/3. Okay, I flipped the two sides of the equation. That's fine, you can do that. It's still true. I just like to have r on the left side here. But anyway, if we simplify here, 6 times 4 is 24. So this is equal to 24/3, or 24 divided by 3, which is equal to 8. But don't forget your units. We did solve for a rate, and our units are miles per hour. So our answer here is that the speed is 8 miles per hour. That is the cross-country runner's running speed if they are moving in uniform motion when running 6 miles in 45 minutes. Okay, so this was an example of one of the more basic types of uniform motion problems, but a lot of uniform motion problems that you will encounter won't just feature one object in motion, like we saw here, they will feature two objects in motion. And so we're going to look at examples of that in just a little bit, but first, there are some things that you want to be aware of before you start to try to solve those types of uniform motion problems. And so here's what you want to know. Here are some tips for solving uniform motion problems that involve two objects in motion. The first tip is that when two objects are moving in opposite directions, then the rate at which the distance between them is increasing is the sum of the speeds of the two objects. All right, so for example, let's say we have two planes that are flying away from each other. They're both flying in uniform motion, meaning that they have constant speeds and they're traveling in a straight line. As those planes fly away from each other, there will be a certain amount of distance between them. And the rate at which that distance between the two planes is changing is just going to be the sum of the two rates for the planes. Okay, so this plane is moving 250 miles per hour in this direction, and this plane is flying at 350 miles per hour in this direction. And so if you add those two speeds together, 250 plus 350, that gives you 600, which means that 600 miles per hour is the rate at which the distance between those two planes is changing. Okay, that's something that you may need to use for a uniform motion problem involving two moving objects. But now, in a similar manner, when two objects are moving toward each other, the distance between them is decreasing at a rate equal to the sum of the speeds of the two objects. Okay, so for example, once again, we have our two planes that are flying in uniform motion, except now, instead of flying away from each other, they're flying towards each other. This plane is flying at 300 miles per hour in this direction, and this plane is flying at 400 miles per hour in this direction. And so the distance between those two planes, which is getting smaller in this case because the planes are getting closer to each other, the rate at which that distance is changing is just equal to the sum of those two rates. So take 300 plus 400, and you get 700 miles per hour. That is the rate at which that distance is changing. Okay, so in both cases, to find the rate at which the distance is changing between two objects, whether they're flying away from each other or towards each other, you can find that rate by just adding the two speeds together for those two objects. All right, really the only difference is that in this scenario, that distance is getting bigger, and in this scenario, that distance is getting smaller. All right, and so this will become useful when you're dealing with a uniform motion problem that involves two moving objects and you need to solve for something related to the distance between them. Okay, so you'll see that in our next example. But before we look at it, one more set of tips I want to give you here on uniform motion problems. It's also important to keep in mind that an object's speed can be affected by their environment. And so what do I mean by that? Well, consider this scenario where we have a boat that is traveling in water. That boat, when the motor is on, can travel 10 miles per hour in this direction. And so that would be its speed, but that speed could be increased or decreased depending on the current of the water. And so in this scenario right here, the water current is 4 miles per hour in this direction, right? That's the direction that the water is moving. And so because both the boat and the water are moving in the same direction, the total speed of the boat will be the sum of those speeds. All right, the water is moving in this direction, which will make the boat move faster. The total speed for the boat here would be 10 plus 4, giving us 14 miles per hour. Okay, so when the boat is moving with the current, you add the speed of the current to the speed of the boat to get the total speed that you would use in your calculations. But now what if the boat is moving in the opposite direction of the current, right? In this scenario here, the boat is still traveling at 10 miles per hour in this direction, but now the current of the water is in the opposite direction. Well, in this case, the water current is going to slow the boat down, specifically by that amount of 4 miles per hour. All right, you would subtract the speed of the current from the speed of the boat. All right, the overall speed of the boat here, the object in motion, would be 10 minus 4, giving us 6 miles per hour. All right, so once again, to recap, if you have an object in motion in a particular direction, and there's something in its environment, such as a water current for a boat, that also has a speed and it's in the same direction, you add those two speeds together to get the total speed of the object in motion. But if they're in opposite directions, then you subtract the speed of the current or whatever else is affecting your object from the actual speed of the object. And notice that in each case, if the boat turned off its motor, meaning that it would not have a speed of 10 miles per hour in this direction, it would just be 0 miles per hour and not heading in any direction. If that was the case, the boat would still move because of the water current. All right, this boat, if it shut off its motor, would be heading 4 miles per hour in this direction. It would go along with the current of the water. In the same way, in this scenario, if this boat shut off its motor, it would travel at 4 miles per hour in this direction. It would follow the current of the water. All right, and so that's it for this tip. This is not something that you will see a lot of in uniform motion problems here in algebra, but it is something that you will see from time to time, so I did want to talk about it here. But now that we've talked about all this, let's take a look at an example of a uniform motion problem where there are two objects in motion. Hey, real quick, before we get to the next part of this lesson, if you find my videos here at JK Math to be helpful, then I'd like to invite you to join my membership site JK Math Plus, where you get access to many perks, including bonus content and my exclusive community. The bonus content includes dark mode versions of my videos, extra example problems, and more, while the community is a private space online where you can post questions, have discussions, and study together with me and other members. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out, as it's a great way to support me in the tutorials I make, as well as a great way for you to learn math better. But for now, let's get back to the lesson. Alright, so for this example, we are told that two cars start from the same point and move in opposite directions. The car moving west is traveling 45 miles per hour, and the car moving east is traveling 60 miles per hour. In how many hours will the cars be 210 miles apart? Okay, so the first thing that I recommend you do for a problem like this is draw yourself a little picture. So that's what I'm going to do here. I'm going to have two cars that are moving in opposite directions. And so here are those two cars. They both start at the same point and travel away from each other, right, in opposite directions. One of the cars is moving west at 45 miles per hour. So that would be this one. We're traveling at 45 miles per hour. And then the other car moving east, which would be this one, is traveling at 60 miles per hour. So this car is traveling this way at 60 miles per hour. And then what the problem wants to know is in how many hours will these two cars be 210 miles apart? In other words, when will the distance between those two cars be 210 miles? All right, and so this is a uniform motion problem involving the distance between two objects in uniform motion, which means that when we use our formula of d equals a rate of motion times t, everything in this equation should be related to that distance. Okay, this distance d right here would be 210 miles. We are given that right here in the problem. All right, the distance between the two cars that we are interested in here is 210 miles. And then what we're solving for is the amount of time, right? We want to know in how many hours will the cars have that distance between them, which means the only thing we haven't accounted for yet is the rate at which the distance is changing with respect to time. And so you might be tempted in this case to either use 45 miles per hour or 60 miles per hour. But again, remember that we're talking about the distance between these two cars. And thinking about the tips I showed you earlier, we can actually determine the rate at which that distance is changing. It's not going to be 45 or 60 miles per hour. It's going to be the sum of those two rates. All right, for two objects in uniform motion moving away from each other, the rate at which the distance between them is changing is the sum or the addition of the two speeds for those objects, or the two rates. Okay, so the rate for the distance here would be equal to 45 miles per hour plus 60 miles per hour, which gives you a total of 105 miles per hour. So now we can set up this equation and solve for the value of t, the amount of hours that it will take for the two cars to be 210 miles apart. So let's set it up. The distance d is 210, so we have 210 is equal to the rate r, the rate at which that distance is changing, which we have determined is 105 miles per hour. So we'll have 105 multiplied by t. Okay, and so now we're almost done. In order to solve for t here, we just need to divide both sides of the equation by that coefficient, or that constant being multiplied by t. So if we divide both sides of the equation by 105, these 105s will cancel out, just leaving you with t, because anything divided by itself is 1. And so we'll get that t is equal to 210 divided by 105, right? That's what we have here. T is equal to 210 divided by 105. And this will actually simplify very nicely. 210 divided by 105 is 2. If you multiply 105 by 2, you will get 210. All right, so we get 2 for the value of t, or more specifically, don't forget your units, that would be an amount of hours, so t is equal to 2 hours. That is the final answer to this uniform motion problem. If you have two cars traveling away from one another in uniform motion, where one is traveling at 45 miles per hour and the other is traveling at 60 miles per hour, it will take 2 hours for those two cars to be 210 miles apart. Okay, let's take a look at one more example for this video. Okay, so for our last example, we have a truck leaves a town traveling 35 miles per hour. 2 hours later, a second truck leaves the same town on the same road traveling at 55 miles per hour. How many hours after the second truck leaves will the second truck pass the first? Okay, so this problem is a little bit more involved than any of our previous examples. This sort of represents the hardest that these uniform motion problems will get here in algebra. Okay, this is the pinnacle of these problems, and they're really going to test your problem solving and equation solving skills. But the good news is it's nothing that we can't handle. It's totally doable. We just have to organize our information and determine what we're actually going to solve for here. And so first of all, let's make sure we know what's going on in the problem here. For one thing, we know that there are two objects in motion, right? There's one truck that leaves town at 35 miles per hour, and then later on, there is a second truck that leaves the same town on the same road, traveling at 55 miles per hour. So I'm just going to start by drawing a little picture involving these two trucks. And so here they are. The first truck is traveling at 35 miles per hour, and the second truck is traveling at 55 miles per hour. But the important thing to remember here is that this second truck does not start moving at the same time as the first truck, right? It starts moving 2 hours later. And then that's all the information that we've been given here, which doesn't seem like a lot, right? We don't really have a ton of information to work with here. And so how do we use our equation of d equals r times t, right? The uniform motion formula that we used in our previous examples. Well, in a situation like this where it's not entirely clear how you want to set up that equation, I think it can be helpful to set up a chart or a table similar to what we've set up for other application problems in algebra. If you watched my videos on percent mixture problems or value mixture problems, this will look familiar. What I want to do is set up a chart involving the values for these two different trucks. So here's what that will look like. We have truck 1 and then truck 2. And then we're going to make a chart where we put in the values for that equation, where we have r, the rate, times the amount of time equal to the distance. Okay, and so let's figure out what each of those values are. And the easiest values to fill in here will be the rates r, because we do know them, right? The speed of truck 1 is 35 miles per hour, and the speed of truck 2 is 55 miles per hour. So we have 35 and 55. Okay, but then what about the time? This is where things get tricky. This is why drawing this chart is helpful, because in this problem, we don't really know an amount of time or an amount of distance. Both of those things are unknown, so it's not as easy as just setting up one equation and solving for an unknown value. We don't know anything about the distance between these two trucks, and we don't know the specific amount of time. All we know is that the second truck starts moving 2 hours after this truck. Okay, and so what we're probably going to have to do here is assign a variable to the amount of time. But the amount of time for each of these trucks will not be the same because they start at different times. All right, so here's what I'm going to do. In this problem, what are we actually solving for? Well, we want to know how many hours after the second truck leaves will the second truck pass the first. So all of that is about the second truck. So I'm going to let the amount of time for the second truck be equal to t. Okay, I'm going to let that variable t represent the amount of time for truck 2. And so what does that tell us about truck 1? Well, remember, truck 1 starts moving 2 hours before truck 2, right? It takes 2 hours after this truck starts moving for this truck to start moving. So whatever amount of time this truck is moving for, truck 2, we're saying that that's t, truck 1 will be moving for that amount of time plus 2 hours. All right, we would say that the amount of time for truck 1 is t plus 2. Okay, I hope that makes sense. We're letting t be the amount of time in hours that truck 2 is moving for, and since it started 2 hours later than truck 1, then truck 1 has to be moving for that amount of time plus 2 extra hours. Okay, and so now we filled in the two columns for r and t, and we know that r times t is equal to d, the distance, so now we can fill in these values as well. For truck 1, d will be equal to 35 times t plus 2, and for truck 2, the distance will be equal to 55 times t. But now what do we do with that information? Well, remember what's going on in this problem. We want to know how many hours after the second truck leaves will the second truck pass the first. In other words, when is the distance traveled for the two trucks the same? Okay, when this truck starts moving, it's the only truck moving, right? It's moving at 35 miles per hour in one direction when it leaves town. So it has a head start over this truck. But then 2 hours later, this truck starts moving at a faster speed. So eventually, it's going to catch up to the other truck. Their distances from where they started at some point will be the same before this truck eventually overtakes this one. So what we want to do here is figure out when is the distance for these two trucks equal. That is going to give us the value of t that we're looking for here. That will tell us how many hours after that second truck leaves will it pass the first one, when their distances are the same. So we can set up an equation where we set this distance for truck 1 equal to this distance for truck 2. So doing that here, we'll have 35 times t plus 2 is equal to 55 times t. And now we have an equation that we know how to solve using our equation solving skills developed earlier in algebra, right? We have an equation with one unknown variable of t, and so we can solve for it. And the first step to do that here would be to get rid of these parentheses. So distribute 35 through this quantity. You want to multiply 35 by t, and then multiply it by 2. So if you do that, you'll get 35t plus 35 times 2, which is 70, and that will be equal to 55t. Then what we want to do is just have one term with t in it, right? We have 35t over here, and then on this side of the equation, we have 55t. So what I'm going to do is subtract one of those terms from both sides of the equation so that we can combine them. And in this case, let's get rid of 35t from this side of the equation. Let's subtract 35t from both sides. If we do that, these will cancel out because 35t minus itself is 0, and you'll just be left with 70 is equal to 55t minus 35t, which is 20t. All right, and then we can solve for t by dividing both sides by 20. We can get rid of that coefficient of t, which will isolate it, and then we'll know what that value of t is. So continuing our work over here, remember that we're dividing both sides by 20, which will give us that t is equal to 70 divided by 20, right? These 20s will cancel out, so you'll just have t, and t will be equal to 70 divided by 20, or 7 halves, right? This fraction could be reduced to 7 halves. Both 70 and 20 are divisible by 10. 70 divided by 10 is 7, 20 divided by 10 is 2, but then as a decimal, t would be equal to 3.5, or 3.5. Okay, 7 divided by 2 is equal to 3.5, and this is an amount of time, so the units will be in hours, because that's what was involved in our rates for speed, right? We had 35 miles per hour and 55 miles per hour. Not to mention that our value of time was also based on hours, because for truck 1, we said that the amount of time was t plus 2, where 2 was in hours, okay? So t equals 3.5 hours is our final answer here. Remember that we let t be the amount of time for truck 2, which is exactly what we wanted to find here. We have now determined that if truck 1 is moving at 35 miles per hour, and then 2 hours later, truck 2 starts moving at 55 miles per hour, it will eventually catch up to that truck and then overtake it after 3.5 hours. That is what we have found here. Okay, and so that is it for this problem. Just a side note here, you could solve this a different way depending on how you assign these values of t. What I mean by that is maybe instead of saying that truck 1 was t plus 2 and truck 2 was t, you could have done this. You could have said that the amount of time for truck 1 was t, and so whatever that amount of time was, truck 2 would have 2 less hours, right? Because truck 2 leaves 2 hours later. So whatever the amount of time is for truck 1, truck 2 would have that amount of time minus 2. And so if you set it up that way, it would change these amounts for the distance. You would have 35 times t for this distance, and then 55 times t minus 2 for this distance. And then you could still set those two distances equal to each other to form an equation where you could solve for t. But then you just have to be careful there and remember that that t that you solved for would be this t right here, the amount of time for truck 1. But the problem wants you to know the amount of time for truck 2, right? It says how many hours after the second truck leaves will the second truck pass the first. So that's talking about the amount of time for truck 2. So once you have solved for the value of t, if you set it up this way, remember that truck 2 has an amount of time of t minus 2. So whatever you get for t, you would subtract 2 from it, and you should get the same answer of 3.5 hours. Okay, so just know that there are multiple ways to do these problems sometimes. It's all about your preference on how you want to set it up. This is how I did it here, with truck 2 being t and truck 1 being t plus 2 for their amounts of time, but you could do it that other way as well. Okay, but now that's it for this example, and this was also the last example for this lesson. But if you do want to get some more practice solving a variety of uniform motion problems, feel free to check out my examples video for this topic that I'll have linked here on the screen. If you have any questions, please let me know in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.